Hello and welcome to Brunei Math Club. In this video, we show how to solve a system of simultaneous linear equations such as this one in a systematic manner, and we also show how to represent such equations using a matrix. Okay, let's start. First of all, let's summarize these equations in terms of a matrix and vectors. That is, take the coefficients on the left-hand side, we make a matrix 3, -1, 2, -1, 1, -6, 2, -1, 6. And the left-hand side can be expressed as a product between this matrix and the vector of xyz. And the right-hand side is just a vector of constants. So 3 equations becomes 1 equations, but with a matrix and 2 vectors. This matrix on the left-hand side is called the coefficient matrix, and this is unknown vector, and this is constant term vector. We next squash this entire equation, into one matrix. So just skip this unknown vector and make the matrix consisting of this part and this part. 3, -1, 2, -1, 1, -6, 2, -1, 6, and 1, -5, 7. This is called an augmented coefficient matrix, or just augmented matrix. So, to recap, we have these equations on one side and this matrix on the other side. So, now let's solve these simultaneous equations in a systematic manner. To begin with, let's number these equations. Okay, now let's multiply the second equation by -1, and we get these equations. So the first one and the third one are unchanged, only the second one changed. And the corresponding augmented matrix becomes this. So note that it seems like we just apply the same operation. So we multiply the second row, this one, by -1 to get this one. And the coefficients are the same, right? So we have these coefficients and these constants. So we apply the equivalent operation here. And next, let's swap the first row and the second row. So in this case, we swap 1 and 2, and we get this. So the third row doesn't change, same for this augmented matrix, but we switched the places of the first and the second rows. And same here for the augmented matrix. So this system of equations became this, and this matrix became this as a result of this operation. And next, let's add to the second row the first row multiplied by -3. But don't change the first row. We only change the second row. Okay, we replace the second row by this operation, and we get this. Since the first row was multiplied by -3, and we added that to the second row, so -3x plus +3x becomes 0. So the x disappear here in the second row. Otherwise, the first row and the third row, they are unchanged. And same for this augmented matrix. And next, let's add to the third row the first row multiplied by -2. That will eliminate this x from the third row. So we get this, and x disappears here. The first row doesn't change, and this coefficient is 0. Next, let's multiply the second row by 1/2. So second row times 1/2. This changes the second row to this. So this is the coefficient is now 1 for y and -8 for z. And the constant term is -7 now. And next, let's add to the third row the second row times -1 to get this. So now from the third row, y disappeared. X wasn't there already. And remember, by this operation, we don't change the second row. Only the third row is changed. And similarly, the corresponding augmented matrix becomes like this. So 0, 0, and only the coefficient for z is here. That is 2. And next, let's add to the first row the second row times 1. And of course, without changing the second row, only change the first row. And we get this. So y is gone from the first row, and accordingly, this coefficient for y is 0. And next, let's multiply the third row by 1/2, so that the coefficient for z becomes 1. And at this point, we know the value of z, which is 2. And now, let's eliminate the coefficient for z in the first row. That can be done by adding to the first row the third row times 2. As a result, we have this, and we now know the value of x, which is 2. And the corresponding augmented matrix becomes 1, 0, 0, and 2. So this 1 is the coefficient for x, and 2 is the constant term. And finally, let's get rid of this coefficient for z in the second row. That can be done by adding to the second row the third row times 8. And we get this. So now we know the value of y, that is 9. And the augmented coefficient matrix becomes 0, 1, 0 for the left part and 9 for the right part. Thus, we have solved the system of simultaneous linear equations. Now, let's review the process of solving these equations. In the process, we have applied some primitive operations, such as multiplying a row by some constant, or swapping two rows, or adding to one row another row times some constant. And we don't change this row, but we only change this row, okay? And if you look all the way, those are the only kinds of operations we have performed. So let's summarize this. First, we swap the ith row and the jth row. So if we have a matrix like this, I1, so this is the ith row, AI2, and so on, AIN, and the jth row, AJ1, AJ2, and so on. So we just ignore all of the other rows. As a result of this operation, swapping the ith row and the jth row, we have the matrix. So the original ith row is filled with the jth row of the original matrix. So the ith row becomes AJ1, AJ2, and so on, AJN. And the jth row becomes AI1, AI2, and so on, AIN. So this is the new ith row, and this is the new jth row. And the second operation was multiplying the ith row by some constant. The constant should not be 0. So if we have a matrix like AI1, AI2, so this is the ith row, then as a result of this operation, the new matrix becomes CAI1, CAI2, and so on, CIN. So this is the new ith row. And the last operation, the third one, is adding to the ith row a constant multiple of the jth row. And I should not be equal to j. By the way, in this case, I should not be equal to j, because otherwise it doesn't change anything. Anyway, so if we have a matrix like AI1, AI2, and so on, AIN, so this is the ith row, so AJ1, AJ2, and so on, AJN, and this is the jth row. Then, as a result of this operation, then the new matrix becomes, so all the other rows are the same, and the ith row is changed. So that's AI1 plus A. So A is this constant times AJ1, and the second column AI2 plus A times AJ2, and so on. And AIN plus A times AJN. So this is the ith row. And what's important is the jth row is unchanged. So AJ1, AJ2, and so on, AJN. So in the new matrix, only the ith row has been changed. These three operations, swapping two rows, multiplying one row, and adding to one row constant multiple of another row, they are called elementary row operations. So by combining these three operations in some order, we can solve any system of simultaneous linear equations. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.